Recently, 3i Atlas shows triple jet configuration. Yes, triple jet. Let me tell you. 3 days ago, January 7th, 2026, Hubble captured something extraordinary. An image that has reignited one of the most fascinating debates in modern astronomy. The clearest view yet of interstellar object 3i Atlas reveals a structure that shouldn't exist, according to conventional comet physics. A triple jet configuration, perfectly symmetric, with a dominant feature pointing directly toward the Sun. Not away from it as every comet we've ever studied does, toward it. And when processed using specialized filters designed to reveal hidden structures, the geometry becomes impossible to dismiss as coincidence. Hit like and subscribe for a more sleepy explanation. The January 7th Hubble image represents our clearest look yet at 3i Atlas. On that date, Hubble captured its latest series of observations of this interstellar visitor. The raw image, the unprocessed data coming directly from the telescope, shows what appears to be a standard cometary coma, a fuzzy glowing cloud surrounding a bright central nucleus. Nothing unusual at first glance. This is what comets look like. This is what we expect to see when volatile ices sublimate under solar heating, releasing gas and dust that forms the characteristic diffuse envelope that makes comets visible across vast distances despite their relatively small solid cores. But astronomer and image analyst Tony Scarato applied a specialized processing technique to this raw image, a method called the Larsen-Saccanina rotational gradient filter. This isn't arbitrary image manipulation. This is a rigorous analytical tool that astronomers have used for decades to study cometary structure. What it does is remove the circularly symmetric glow around the nucleus, the diffuse background that dominates the visual appearance, revealing structures that would otherwise remain hidden beneath the brighter coma. It's like using polarized sunglasses to see through glare on water's surface to the structures beneath. You're not creating artifacts, you're removing visual noise that obscures real features. And what emerged when Scarato applied this filter stopped researchers in their tracks. A triple jet structure emanating from the nucleus. 3 distinct features separated by equal angles from each other, approximately 120 degrees apart. Perfect geometric symmetry, not approximate, not roughly equal. But precise threefold symmetry that you'd expect from engineered structure designed for balanced thrust, or from some natural process that we don't understand but that operates according to principles, producing exact geometric relationships rather than the irregular chaotic patterns that random sublimation typically creates. The dominant feature, the one that immediately captures attention, and that has become the focus of intense analysis and debate, is what astronomers call an anti-tail, a jet extending approximately 400,000 kilometers sunward. That's nearly the distance from Earth to the Moon, not trailing away from the Sun as radiation pressure and solar wind would dictate according to every principle of cometary physics we've established through studying hundreds of comets over centuries, but pointing directly toward it. Toward the Sun, against the forces that should be pushing material away, maintaining coherent beam structure across distances that should cause dispersion and randomization if this were just gas and dust being released through sublimation. According to Professor Loeb's analysis published on Medium just days ago, and I'll link to his full technical articles in the description, because the mathematical details matter, and because you deserve access to primary sources rather than just my summary, this anti-tail is tightly collimated, beam-like in its structure, more than 10 times longer than it is wide. That aspect ratio, that degree of focus and directionality, is extraordinarily difficult to achieve through natural gas dynamics. When comets release material through sublimation, when sunlight heats ice pockets causing them to vaporize and eject gas-carrying dust particles, the resulting jets typically expand rapidly. Follow ballistic trajectories, disperse through interaction with solar wind and through their own internal pressure. Don't maintain narrow-focused beams across hundreds of thousands of kilometers. The 2 minor jets are equally puzzling. They're not oriented away from the Sun either as traditional cometary tails would be. Comets typically show 2 types of tails. Dust tails that follow the comet's orbital path because the dust particles have mass and momentum, and ion tails that point directly away from the Sun because the charged particles get pushed by solar wind. But 3i Atlas's minor jets don't fit either pattern. Instead, they maintain fixed angular separation from the anti-tail, creating that threefold symmetric pattern, rotating with the object, maintaining their 120-degree spacing regardless of the comet's position relative to the Sun or its rotational phase. This isn't the first time Hubble has observed unusual features on 3I Atlas. Previous images from July, November and December 2025 showed similar structures, but the January 7th image is the clearest yet, the highest resolution, the most detailed view of an anomaly that has persisted throughout 3I Atlas's journey through our solar system. And persistence is key here, because it eliminates many natural explanations that might account for transient anomalies. A momentary outgassing event could be dismissed as natural variation, a transient burst of activity as the comet rotates and different areas of its surface face the Sun. Comets do this all the time. They show sudden increases in brightness, temporary jet formations, changes in activity level as their rotation brings fresh ice into sunlight, or as subsurface ice pockets break through surface layers and suddenly release stored gas. All normal, all explicable through well-understood physics. But we're not talking about momentary phenomenon. We're talking about structure that has remained coherent and sunward pointing across millions of kilometers of space. Through perihelion passage, the closest approach to the Sun when solar heating is most intense, and when cometary activity typically peaks and becomes most chaotic. And now, as the object recedes from the Sun, as solar distance increases and heating decreases and activity should be waning, the structure persists. That's not transient. That's not random. That's sustained directed behavior that requires explanation beyond ice is sublimating. Let me explain what an antitail actually is, and why 3I Atlas's version is so problematic for conventional comet physics. In normal comets, tails form when volatile ices on the nucleus sublimate. Solid ice transitions directly to gas, sublimation, without going through liquid phase. This happens because comets exist in vacuum where liquid phase isn't stable. As solar heat increases, this gas carrying dust particles with it gets pushed away from the Sun by two forces working together. First, solar radiation pressure. Photons carry momentum. When they hit dust particles and get absorbed or reflected, they transfer that momentum to the particles. The effect is tiny for any individual photon-particle interaction. But when you have the Sun's enormous photon flux hitting trillions of dust particles, the cumulative force becomes significant, pushes the dust away from the Sun, creates the classic curved dust tail that we see in comet photographs. Second, solar wind. The stream of charged particles, primarily protons and electrons, flowing outward from the Sun at speeds of several hundred kilometers per second. When this wind encounters gas molecules in the cometary coma, it interacts electromagnetically, ionizes the molecules, carries them along with the wind flow, creates the straight ion tail that points directly away from the Sun, regardless of the comet's motion. This is one of the most fundamental and reliable behaviors in cometary physics. Comet tails always point away from the Sun. Always. Without exception, in hundreds of years of observation across hundreds of comets, anti-tails can occur, but they're almost always optical illusions. Projection effects caused by viewing geometry. When we observe a comet from a specific angle, when Earth's position relative to the comet's orbit creates particular geometric configuration, dust particles left behind in the comet's orbital plane can appear to extend toward the Sun, even though they're actually part of the tail structure pointing away. It's perspective trick. Like looking at curved line from an angle that makes it appear straight, or looking at three-dimensional object from vantage point, where depth information is lost and spatial relationships appear different from what they actually are. The phenomenon isn't real, it's perspective. It's how we're viewing actually normal tail structure from a particular angle that creates illusion of sunward extension, and we can verify this is what's happening by observing from different angles, or by waiting for Earth's position to change and watching the apparent anti-tail disappear or shift in ways that confirm it was projection artifact rather than real physical structure. But 3I Atlas's anti-tail isn't optical illusion. We know this with high confidence through multiple lines of evidence. When Hubble first imaged the object on July 21, 2025, the observing angle, the geometric configuration between Earth, 3I Atlas, and the Sun, was only 10 degrees off the sunward direction. That's nearly ideal geometry for detecting real anti-tail if one exists, but also geometry where projection effects would be minimal, because we're looking almost directly along the Sun-comet line, rather than viewing from angle where dust plane projections could create false anti-tail appearance. Simple trigonometry accounting for the viewing geometry, accounting for the known positions of Earth and 3-eye Atlas and the Sun at that observation date, revealed that the true elongation of the structure, its actual physical extent in space rather than its projected appearance in our images, was approximately 5.8 times greater than it appeared in the projected image, making it more than 11 times longer than wide, a highly collimated beam structure, not the diffuse dispersing cloud that natural sublimation produces, not the curved sheet of particles that projection effects create, but focused beam maintaining coherence across distances where thermal velocities and solar wind interactions should cause rapid expansion and dispersion. And here's the critical point that eliminates the optical illusion explanation definitively. Multiple observations at different dates, different distances from the Sun, different viewing angles have all confirmed the same feature. If this were projection effect, it would change appearance dramatically as our viewing angle changed. The apparent anti-tail would lengthen or shorten, would appear or disappear entirely at certain geometries, would show the variations that projection artifacts necessarily display, because they're artifacts of viewing geometry rather than real structures. It hasn't. According to Loeb's analysis published this week, the January 2026 analysis examining the latest Hubble data, the anti-tail remained prominent in the January 7th image, despite 3-eye Atlas now being significantly farther from the Sun than during perihelion. The solar heating that drives cometary activity should be decreasing, the sublimation rates should be dropping, the jets should be weakening, dispersing, changing orientation as the comet rotates and as activity wanes with increasing solar distance. Instead, we see the same tightly focused sunward jet maintaining its collimation across vast distances, maintaining its orientation toward the Sun despite the object's rotation, maintaining its coherence despite the decreasing solar heating that should reduce the gas production rate that would be necessary to sustain such structure through purely natural sublimation processes. This is anomalous, genuinely, undeniably anomalous in ways that demand explanation rather than dismissal. Now we get to what Professor Loeb considers one of the most statistically significant aspects of this entire phenomenon, the rotation axis alignment. A paper published in Astronomy and Astrophysics, that's one of the premier peer-reviewed journals in the field, by Sarah Ricard-Licandro and colleagues documented a wobbling pattern in the anti-tail jet during July and August 2025. Not random wobbling, not chaotic variations, but systematic periodic wobbling that indicates specific geometric relationship between the jet source and the object's rotation. This wobble revealed that the jet base, the location on the nucleus where the gas is being emitted that creates the anti-tail, is offset by less than 8 degrees from the poles of the object's rotation axis. Think of it like this. Imagine 3-eye Atlas is spinning like a top. The rotation axis is the line through the centre around which it spins. The poles are where that axis intersects the surface. The jet is coming from location very close to one of those poles. Within 8 degrees of the pole, as 3-eye Atlas rotates, the jet precesses, sweeps out a cone in space, like lighthouse beam rotating as the lighthouse spins. But it's a very narrow cone because the source is so close to the rotation axis. If the source were at the equator, far from the poles, rotation would cause the jet to sweep through enormous arcs. The beam would appear and disappear as the source region rotated through day and night. We'd see dramatic variations in the anti-tail's appearance and orientation as the rotation brought the source into and out of view and changed its orientation relative to our line of sight. But we don't see that. We see persistent beam with only slight wobbling, which means the source must be near the pole, must be located where rotation creates minimal change in the jet's direction relative to our viewing angle. That's what the Ricard-Licandro paper established through careful analysis of the wobble pattern's amplitude and period. The jet base is within 8 degrees of the rotational pole. That's geometric fact derived from observations rather than being speculation or interpretation. Here's where it gets statistically interesting, where we transition from "that's unusual" to "that's so improbable, it demands special explanation." For this tight collimation to be maintained, for the anti-tail to appear as coherent beam, extending hundreds of thousands of kilometers sunward, rather than as dispersing cloud or wobbling arc, the rotation axis must be nearly aligned with the direction of the Sun. The pole where the jet originates must be pointing approximately toward the Sun. Otherwise, as the object rotates, even if the jet source is at the pole, the rotation would cause the beam to sweep through large angles relative to the sunward direction, would create variations we don't observe. Loeb's calculations, published in multiple Medium articles analysing different observation periods, indicate that the rotation axis is aligned to within approximately 6 to 8 degrees of the sunward direction. Let me repeat that because this is crucial. The spin axis of this interstellar object is pointing at the Sun to within 6 to 8 degrees. For an object that arrived from interstellar space, that had its rotation established billions of years ago through whatever processes formed it or launched it from its home system. That has been tumbling through the galaxy for incomprehensible spans of time, subject to random perturbations from radiation pressure and from gravitational interactions with objects it passed. The probability of that rotation axis randomly being aligned this precisely with the sunward direction when we happen to be observing it is 0.2% to 0.5% depending on the exact measurement uncertainty. That's a 1 in 200 to 1 in 500 chance. Now, one could argue that rare things happen. That 0.2% probability event isn't impossible, that if you observe enough comets eventually you'll see unusual geometries just through statistical chance. That finding one comet in several hundred with unusual axis alignment doesn't necessarily mean anything special about that particular comet. All valid points from purely statistical perspective if we're only looking at this one feature in isolation. But this isn't occurring in isolation. This is where the statistical argument becomes compelling rather than being merely suggestive. The trajectory of 3I Atlas is aligned to within 5 degrees of the ecliptic plane. The ecliptic is the flat disk in which the planets orbit the Sun. It's the plane defined by Earth's orbit and by the original protoplanetary disk from which the solar system formed. For objects that formed in our solar system, being in or near the ecliptic is normal because everything formed from that same rotating disk. But 3I Atlas is interstellar object. It arrived from outside our solar system, from random direction in the galaxy. Interstellar space is three-dimensional. Objects travel in all directions. There's no preferred plane, no reason why trajectory from another star system should happen to align with our solar system's ecliptic plane rather than arriving from any other angle. The probability that random interstellar trajectory happens to be within 5 degrees of our ecliptic plane is approximately 0.2%. Another 1 in 500 chance. Now here's where the mathematics becomes unavoidable. When you have two independent low probability events, the probability that both occur simultaneously is the product of their individual probabilities. This is basic probability theory. If event A has 0.2% probability and event B has 0.2% probability, and they're independent, meaning one doesn't cause or influence the other, then the probability of both A and B occurring is 0.02x, 0.02, 0.0004. That's 0.004%. That's 1 in 250,000. But we need to be more careful with the calculation because the exact probabilities depend on measurement uncertainties and on exactly how we define the alignment thresholds. If we use the more conservative estimates, 6 to 8 degrees for rotation axis alignment, giving us roughly 0.5% probability, and 5 degrees for ecliptic alignment also giving roughly 0.5% probability, then the compound probability is 0.05x 0.05, 0.025. That's 0.25%. That's approximately 1 in 40,000. Loeb's published calculations, accounting for the specific measurement uncertainties and geometric configurations, place the compound probability at approximately 0.001, 1 in 100,000. But let's be conservative. Let's round to 1 in 10,000 because we want to avoid any appearance of overstating the case. Even with that conservative estimate, we're talking about geometric configuration that should occur by random chance in only 1 out of every 10,000 interstellar objects. And we haven't even factored in the other anomalies yet. The arrival timing that brought 3I Atlas close to Mars, Venus and Jupiter, while being unobservable from Earth at perihelion, a geometric configuration that required specific trajectory and timing that further constrains the probability space, the unusually high nickel-to-iron ratio in its gas emissions, compositional signature resembling industrial alloys rather than natural cometary compositions, adding another layer of improbability if we're maintaining that everything is purely natural coincidence. The fact that the same sunward jet persisted both before and after perihelion. Think about what that means geometrically. As comet approaches the Sun, one hemisphere receives intense solar heating. After perihelion, as comet recedes, the opposite hemisphere faces the Sun due to orbital geometry. For the same sunward jet to be visible both approaching and receding requires that similar structures exist at both poles, or requires that the object is somehow maintaining the jet through mechanism that doesn't depend on which hemisphere is currently sunlit. Either way, it adds constraint that further reduces probability of all these features arising through random natural processes. Each anomaly individually might be dismissed, rare but natural. But when you stack them, when you calculate the compound probability of all these unlikely geometries and behaviours occurring simultaneously in a single object, you enter territory where dismissal becomes intellectually difficult. Where saying it's just coincidence requires believing that we're observing something that should occur in roughly 1 out of every 10,000 to 100,000 interstellar objects. And given that we've only detected 3 confirmed interstellar visitors in human history, Oumuamua, 2I Borisov, and now 3I Atlas, finding such rare configuration in our tiny sample is itself statistically remarkable. Loeb isn't claiming definitive evidence of artificial origin. That's important to understand because his position is often mischaracterized as Harvard professor says it's aliens, when what he's actually saying is more nuanced and more scientifically rigorous. He's pointing out that the statistical improbability demands serious investigation rather than casual dismissal. That when you encounter 1 in 10,000 compound probability, you don't just shrug and say weird but probably natural without doing the work to actually demonstrate what natural mechanism could produce these results. That extraordinary claims might require extraordinary evidence, but extraordinary observations also require extraordinary explanations, and simply asserting it's natural without providing mechanism that accounts for the observations is not adequate scientific response. Let's return to that January 7th Hubble image and examine the triple jet structure in detail, because the geometry is even more specific than I've described so far. After applying the Larsen-Sekanina filtering that removes the circularly symmetric coma glow, 3 distinct features emerge from the processed image, the dominant anti-tail which we've discussed extensively, and 2 minor jets positioned at approximately 120 degree separation from each other and from the anti-tail. Perfect threefold symmetry. Why is threefold symmetry significant? Because it's not what you expect from random sublimation on a regularly shaped rotating body. Natural comets have irregular shapes, rough surfaces, random distribution of volatile ice deposits. When such objects rotate and different surface regions receive solar heating, the resulting jets appear at random locations, random orientations, random intensities, depending on where the active ice happens to be located. You might see 1 jet, you might see several jets, but you don't expect to see 3 jets arranged in perfect 120 degree spacing around rotation axis. Threefold symmetry suggests either very specific natural geometry, like crystal structure, with threefold symmetry somehow translated to macroscale comet shape and volatile distribution, or suggests deliberate design, engineered structure where threefold symmetry serves functional purpose, balanced thrust if you're using the jets for propulsion, uniform coverage if you're using them for observation or communication, structural stability if you're dealing with a rotating system that needs to maintain specific orientation. In his January 2026 Medium post analysing Hubble images from November and December, I'm citing these dates because it's important to understand this is ongoing analysis, not single observation, but sustained investigation, tracking the object's behaviour over months. Loeb noted that these minor jets show variability. Their extent changes over the object's 16-hour rotation period, variations of approximately 5,000 kilometres over an 8-hour period, which is half rotation. This variability is actually consistent with normal cometary behaviour, is consistent with thermal velocity of volatile molecules sublimating from ice pockets on a rotating nucleus. Jets turn on when their source regions rotate into sunlight and begin receiving solar heating that drives sublimation. Jets turn off when those same regions rotate into shadow where solar heating ceases and sublimation stops or dramatically slows. This is how comets work. This is what we expect to see. Nothing anomalous here about the minor jets showing rotational variability. But the anti-tail is different. It's an order of magnitude larger than the minor jets, 400,000 kilometers versus maybe 40,000 kilometers for the minor jets. And it shows no corresponding variability with rotation. Despite the object completing a full rotation every 16 hours, despite different surface regions rotating into and out of sunlight, despite the changes in local solar heating that should affect sublimation rates, the anti-tail remains coherent and stable across much longer timescales, doesn't strengthen and weaken with rotation period, doesn't appear and disappear, doesn't show the variations that you'd expect if it were being produced by localized ice pocket that rotates through day-night cycle. For this stability to exist, Loeb argues, the anti-tail source must be located very close to the rotational pole within that 6 to 8 degree cone we discussed. If it were located elsewhere on the surface, at mid-latitudes or near the equator, rotation would cause the jet to sweep through large arcs. The beam would point in different directions as the source region rotates around the axis, would appear and disappear as the source moved through day-night transitions, would show dramatic brightness variations as viewing geometry changed with rotation. Instead, we see lighthouse effect. The jet precesses in a tight cone around the rotation axis, which is itself pointed at the sun. From our viewing angle, this appears as a persistent sunward beam with only slight wobbling, the wobble that Ricard Licandro measured and that confirms the 8 degree offset from the pole. The beam is always roughly sunward because the rotation axis is aligned sunward and the jet source is near that axis. So rotation doesn't significantly change the jet's direction relative to the sun. Natural gas dynamics can absolutely produce jets from rotating comets. This happens all the time. It's well understood physics. Sublimation driven by solar heating creates gas pressure. Gas escapes preferentially from weaker spots in the surface, where ice is closer to the surface or where overlying dust is thinner. Rotation brings different regions into sunlight, creating temporal variations in jet activity. All normal, all explicable, all consistent with what we observe in solar system comets, but having multiple jets in perfect 120 degree symmetry. Combined with rotation axis alignment within 6 to 8 degrees of sunward direction, combined with trajectory alignment within 5 degrees of ecliptic plane, combined with compositional anomalies showing unusual nickel-to-iron ratios, combined with unusual mass-to-brightness ratios that suggest the object is either much denser or much less reflective than typical comets, combined with the persistence of coherent sunward beam that doesn't show rotational variability despite 16-hour spin period, the compound probability keeps shrinking. Each additional constraint, each additional anomaly that needs to be explained simultaneously, multiplies against the already low probabilities from the geometric alignments. And we're not cherry-picking anomalies here. These are all documented features that any comprehensive explanation of 3i Atlas needs to account for. You don't get to pick and choose which observations to explain. You need to explain all of them. Or at minimum, you need to acknowledge which observations your explanation doesn't account for, and provide testable predictions for how those gaps might be filled. It's important to address the scientific debate surrounding 3i Atlas directly and fairly, because this isn't a situation where all scientists agree, and the evidence is unambiguous. There are legitimate differences of interpretation, legitimate debates about what the observations mean, and presenting only one side without acknowledging the other would be intellectually dishonest. So let's talk about NASA's position and about how it differs from Loeb's analysis. NASA held a press conference on November 19, 2025, presenting their assessment of 3i Atlas. Their conclusion, stated clearly and backed by extensive observational data, it behaves like a regular comet. Natural origin. No evidence of artificial construction. This conclusion isn't arbitrary, isn't based on dismissing evidence, is based on extensive data that NASA's researchers have collected and analysed using multiple instruments across multiple wavelengths, spectroscopic analysis showing water and carbon dioxide ice, the same volatile ices that we find in solar system comets, cometary coma structure, the diffuse cloud of gas and dust that's characteristic of ice sublimation, outgassing rates consistent with solar heating. When you calculate how much solar energy the object receives at its distance from the sun, and you calculate how much ice that energy could sublimate, the observed gas production rates match the predictions. These are legitimate observations. These are solid data points supporting natural origin. Anyone claiming to provide comprehensive analysis needs to acknowledge and address these observations, not ignore them because they don't fit preferred narrative. But, and this is where the scientific debate becomes substantive rather than just being matter of interpretation of ambiguous data, Professor Loeb in his January 9th Medium article points out a significant issue with NASA's presentation. The geometric anomalies, the statistical improbabilities we've been discussing, weren't mentioned at the press conference. The rotation axis alignment with its 0.2% probability, the trajectory alignment with its 0.2% probability, the compound probability calculations that drop to 1 in 10,000 or worse. These weren't addressed, weren't discussed, weren't factored into the conclusion that it's a regular comet. Loeb writes, and I'm quoting directly from his Medium article because his words matter and shouldn't be paraphrased in ways that might distort his meaning. Obviously, if one ignores the unexplained anomalies of 3I Atlas, one would conclude that there is nothing surprising about it. The easiest way to argue that we fully understand something is by ignoring what we do not understand about it. This is methodological criticism, not personal attack. This is about how science should operate when confronting anomalous data. In science, we're supposed to address all the data, especially the data that doesn't fit our preferred model, especially the observations that challenge our assumptions, especially the anomalies that would force us to revise our understanding or consider alternative explanations if we take them seriously. If there's a natural explanation for why an interstellar object would have its rotation axis aligned sunward with 0.2% probability, that explanation should be published and peer-reviewed. If there's a natural mechanism that creates perfect 120-degree jet symmetry while maintaining a 10 times larger collimated anti-tail that doesn't vary with rotation, that mechanism should be demonstrated through modelling and simulation. If there's reason to believe the compound probability calculation is wrong, that the events aren't actually independent, or that selection effects make the configuration more likely than it appears, that reasoning should be presented with quantitative analysis supporting the revision. Simply stating it's a natural comet without addressing the geometric anomalies isn't sufficient scientific rigour. It's not how you resolve debates in science. You resolve debates by proposing specific testable mechanisms, by building models that reproduce observations, by making predictions that observations can verify or falsify, by engaging with the full dataset rather than with only the subset that supports your conclusion. Now, does this mean 3I Atlas is artificial? Not necessarily. Nature can be weird, really, genuinely weird. Improbable things do happen. The universe is vast and old and contains far more complexity than our relatively brief scientific investigation has characterized. There are almost certainly natural processes that we don't understand yet, mechanisms that produce results we wouldn't predict based on current models. Phenomena that are rare enough that we haven't observed them in our limited sample of solar system comets, but that occur with some frequency across the galaxy where trillions of comets exist. But, and this is the critical distinction, improbable things that happen repeatedly in the same object, creating compound probabilities approaching 1 in 10,000 or worse, deserve investigation proportional to their improbability. That's what Loeb is advocating for, not jumping to conclusions about alien probes or artificial spacecraft, not claiming definitive proof of technological origin, but proportional investigation, resources allocated to understanding these anomalies that's commensurate with how unlikely the observations are if we're maintaining that everything is natural coincidence. That's what the Galileo project, which Loeb heads, exists specifically for. To investigate potential technosignatures with proper scientific methodology, not to prove aliens exist, not to promote sensational claims about extraterrestrial visitors, but to look carefully at anomalous data using rigorous scientific methods and to determine what it actually represents, to build instruments specifically designed for detecting and characterizing unusual objects, to establish protocols for observation and analysis that can distinguish between natural phenomena we don't understand yet and potential artificial objects if such exist. The project takes its name from Galileo Galilei, who faced similar skepticism when he reported observations that challenged accepted models, who was told his telescopic observations of Jupiter's moons were optical illusions or instrumental artifacts because the prevailing cosmology didn't allow for moons orbiting planets other than Earth. Who was right despite the consensus of his time being wrong because he trusted observations over theory when they conflicted? The parallel is deliberate. The message is that observations should drive theory, not the other way around. That when observations don't match expectations, we need to update the expectations rather than dismissing the observations. We should also discuss the SETI observations because they're directly relevant to the artificial hypothesis, and because they provide important constraints on what 3i Atlas might or might not be. Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence currently operating, funded by Yuri Milner's Breakthrough Initiatives and utilizing some of the world's most sensitive radio telescopes, conducted extensive observations of 3i Atlas specifically to test whether it shows any signs of artificial radio emissions. Using the Green Bank telescope, the largest single-dish radio telescope in the world, located in West Virginia, with a 100-meter diameter dish and receiving systems sensitive across an enormous range of frequencies, they scanned from 900 to 1,670 MHz during 3i Atlas's closest approach to Earth on December 19, 2025. That's optimal time for observation because distance was minimized, meaning signal strength would be maximized if any signals exist. And that frequency range covers many bands where human technology operates, where natural astrophysical sources emit, and where extraterrestrial technology might plausibly transmit if it uses radio. Their results, published in a preliminary paper this month, and again I emphasize preliminary, because scientific process is ongoing and conclusions can be revised as additional data and analysis become available, detected approximately 470,000 candidate signals initially. That sounds like a lot, but the vast majority of those signals are from human sources, satellites broadcasting, cell towers transmitting, radio stations operating, radar systems scanning, aircraft transponders beeping, all the electromagnetic noise that human technological civilization generates constantly, and that pollutes the radio spectrum, making SETI observations challenging. After filtering out human-generated radio interference, after accounting for satellites and other terrestrial sources whose positions and transmissions are catalogued, they were left with 0 candidate technosignatures, 0 signals that couldn't be explained as either human activity or natural astrophysical sources. Their detection sensitivity was 0.7 watts, enough to detect a cell phone signal at 3i Atlas's distance, when it was closest to Earth. That's remarkably sensitive. That means if 3i Atlas had radio transmitter operating at power level comparable to human handheld devices, Breakthrough Listen would have detected it. Their conclusion, stated in the paper, there is currently no evidence to suggest that interstellar objects are anything other than natural astrophysical objects. This is significant evidence against the artificial hypothesis. If 3i Atlas were a functioning spacecraft or probe in the sense that we typically imagine spacecraft, with communication systems maintaining contact with home civilization, with power generation producing electromagnetic emissions as byproducts, with navigation systems requiring radio or other electromagnetic transmissions for positioning or coordination, you'd expect some form of detectable emissions. Communication systems broadcasting back to wherever 3i Atlas came from, power generation signatures, the electromagnetic noise that nuclear reactors or fusion systems or other high-energy processes inevitably produce, navigation systems transmitting or receiving positioning data, internal systems generating radio frequency interference the way all our electronics do, something, anything. But Breakthrough Listen detected nothing, 0 artificial signals within their detection threshold. However, and this is crucial caveat that the Breakthrough Listen team themselves noted in their paper, given the small number of such objects, known only 3 to date, and the plausibility of interstellar probes as a technosignature, thorough study is warranted. They're not dismissing investigation. They're not saying we found nothing, therefore there's nothing to find and we should stop looking. They're saying their radio observations found nothing, but that doesn't close the book on anomalous behavior in other domains. That absence of evidence in the radio spectrum is evidence of absence of radio transmitting technology, but isn't evidence of absence of technology that doesn't rely on radio. Let me unpack what that means practically. A non-functioning derelict wouldn't produce radio signals. If 3i Atlas is ancient probe that exhausted its power centuries or millennia ago, that's coasting on ballistic trajectory established long ago, that no longer has active systems requiring communication or navigation, then it wouldn't be broadcasting, would be electromagnetically silent, would pass breakthrough, listens observations without detection, while still potentially being artificial in origin. A light sail pushed by radiation pressure wouldn't need onboard power beyond what's required for minimal attitude control or deployment mechanisms. Wouldn't need to broadcast communications if it's operating autonomously according to pre-programmed mission profile. Wouldn't generate the electromagnetic signatures that powered spacecraft produce. Could be entirely passive structure, reflective sail and minimal payload, that produces no radio emissions detectable at interstellar distances, yet still constitutes artificial object deliberately constructed and launched by technological civilization. A probe using propulsion technologies we don't understand, technologies that don't generate radio frequency emissions as byproduct, or that shield emissions so effectively that external detectors can't pick them up, would similarly evade radio SETI. If your civilization millions of years more advanced than humanity, if you've developed propulsion and power systems that operate according to physical principles we haven't discovered yet, there's no reason to expect those systems would leak radio waves in ways our 20th century detection technology can intercept. So the absence of radio signals rules out certain types of artificial origin, specifically rules out scenarios where 3i Atlas is actively transmitting radio communications, or where its onboard systems generate detectable radio frequency interference, but doesn't rule out all conceivable artificial scenarios, doesn't definitively establish natural origin, just narrows the possibility space, eliminates some hypotheses while leaving others viable. This is how science works. You test hypotheses. When observations contradict predictions, you reject or modify the hypothesis. Breakthrough Listen's observations are inconsistent with 3i Atlas is spacecraft with radio communication systems, but are consistent with both 3i Atlas is natural comet, and with several artificial scenarios that don't require radio emissions. So we update our probability distributions based on the new evidence, but we don't collapse to certainty in either direction, because the evidence, while informative, isn't definitive. Where does this leave us? With an object displaying multiple statistical anomalies in its geometry and trajectory, the rotation axis alignment, the ecliptic plane alignment, the triple jet symmetry, the collimated anti-tail, but no detected artificial radio signals. Natural origin with unusual characteristics remains the most parsimonious explanation, according to Occam's razor, which tells us to prefer simpler explanations over more complex ones when both fit the observations. Aliens a complicated explanation requiring that extraterrestrial intelligence exists, that they've developed interstellar travel, that they've visited our solar system during the brief window when we're capable of observing them. Natural comet with rare but possible geometric configuration is simpler explanation requiring only that physics we already know about can sometimes produce unlikely results. But, and this is where scientific judgment becomes more art than algorithm, unusual enough to justify continued close observation and analysis, unusual enough that dismissing investigation as waste of resources isn't defensible, unusual enough that the scientific community should be tracking this object carefully, collecting as much data as possible while it remains observable, testing specific predictions that might distinguish between competing hypotheses. Because if the compound probability really is 1 in 10,000, then claiming it's definitely just a comet, nothing to see here, is premature. We should be treating it as potentially the most interesting comet we've ever observed, even if we ultimately conclude it's natural, because the geometry is teaching us something about the range of behaviors that natural processes can produce. What happens next? This is where the story transitions from what we've observed to what we're going to observe, and why the coming months are critical for resolving some of the questions about 3i Atlas. The object is currently in the constellation Cancer, fading as it moves away from the Sun. Current magnitude is approximately 13 to 15.6, depending on observing conditions and on which photometric band you're measuring in. For context, that's far too faint for naked eye observation. You need magnitude 6 or brighter for naked eye visibility under dark skies, but well within range of amateur telescopes under reasonably good conditions. Opposition occurs on January 22nd, 2026, just days from now as I'm recording this. Opposition means the object will be directly opposite the Sun in our sky. When the Sun sets, 3i Atlas rises. It's up all night. But opposition doesn't mean bright in this case because the object is far away and fading. It just means optimal viewing geometry for Earth-based observers because we're not fighting scattered sunlight or atmospheric distortion from looking close to the horizon. You'll need an 8 to 12-inch telescope under dark skies to visually observe it. That's not huge professional equipment, that's high-end amateur gear. If you're a serious astrophotographer, or if you have access to university observatory, or if you're part of amateur astronomy club with good equipment, you can potentially observe this object yourself. For astrophotographers, long exposures, we're talking several minutes of integration time, can still capture the coma, and possibly even hints of the jet structures we've been discussing, if you apply proper image processing techniques like the Larsen-Sechenina filtering that revealed them in Hubble images. But the real action, the observation that might definitively answer whether 3I Atlas is natural or something else, comes in March 16th, 2026, closest approach to Jupiter. Distance 0.358 AU. That's approximately 53.6 million kilometers from Jupiter's center. For scale, that's closer than Mercury is to the Sun. That's close enough that Jupiter's gravity will definitely perturb 3I Atlas's trajectory. We'll change its velocity and direction through gravitational interaction. We'll provide natural experiment testing whether the object responds to gravitational forces the way natural comets should, or whether it shows propulsive corrections that would indicate active navigation. On March 17th, just one day after closest approach to Jupiter, 3I Atlas passes within 30 million kilometers of Eupheme, one of Jupiter's irregular outer moons. Eupheme is tiny, just 2 kilometers in diameter, orbiting Jupiter in retrograde direction, at a distance of about 20 million kilometers from the planet. It's one of the Ananke group, cluster of irregular satellites that are thought to be captured asteroids or fragments of larger body that broke up near Jupiter. Why does encounter with this tiny moon matter? Because Loeb has stated publicly, in his Medium articles and in interviews, that if 3I Atlas releases daughter objects that enter orbit around Jupiter during this encounter, it would constitute strong evidence for technological origin. That's a testable prediction. That's falsifiable hypothesis. That's exactly what science should be doing. Making specific predictions about future observations that would distinguish between competing explanations. Think about why this prediction matters. Natural comets don't release daughter objects that enter orbit around planets they're passing. They might fragment through tidal forces if they pass too close, but fragments would continue on similar trajectories to the parent body, maybe slightly perturbed by the tidal disruption. They wouldn't enter stable orbits around the planet requiring precise velocity changes that only propulsion or extremely unlikely gravitational captures could provide. But if 3I Atlas is artificial, if it's probe or mothership sent to study the solar system, releasing smaller probes into Jupiter orbit during close approach would be logical operational profile, would enable long-term observation of Jupiter system while parent craft continues on interstellar trajectory, would be exactly what human mission planners would do if we were sending probe to study distant star system, release orbital assets at planets of interest, while using the gravity assist to continue to next targets. So if it happens, if we observe objects separating from 3I Atlas and establishing stable orbits around Jupiter, rather than continuing on hyperbolic escape trajectories, that would be extraordinarily difficult to explain through natural means. Would require either multiple extremely unlikely gravitational captures occurring simultaneously, or would require acknowledging propulsion capability that natural comets don't possess. Would shift probability distributions dramatically toward artificial hypothesis, even though it wouldn't constitute absolute proof. You could still construct elaborate natural scenarios, but they'd become increasingly contrived. If it doesn't happen, if 3I Atlas simply passes Jupiter and continues outbound with only the gravitational deflection that orbital mechanics predicts without any daughter objects appearing in Jupiter orbit, that strongly supports natural origin. Doesn't prove it definitively because maybe artificial probe doesn't have mission profile that includes releasing Jupiter orbiters, but absence of daughter objects would be what we expect from natural comet and wouldn't be what Loeb's technological hypothesis predicts. Either way, we'll have more data, more observations, more constraints on what this object is and isn't. And that's how science progresses, through testable predictions that subsequent observations can verify or falsify, through narrowing possibility space until one explanation clearly fits better than alternatives, through following evidence wherever it leads, rather than deciding in advance what we want to be true. After Jupiter, assuming 3I Atlas continues on its current trajectory, without releasing daughter objects or making propulsive maneuvers that would indicate artificial control, the long goodbye begins. The object will continue outward through the solar system on its way back to interstellar space. Saturn system in late 2026, Uranus in 2027, Neptune in 2028. Each of these encounters provides additional opportunities for observation, additional chances to detect anomalous behavior, additional data points to test whether the trajectory matches gravitational predictions or shows deviations requiring non-gravitational explanations. By the time 3I Atlas reaches the inner Oort cloud around the year 2189, no human alive today will be here to witness it. We'll all be long dead. The civilization that observes 3I Atlas entering the Oort cloud will be as different from us as we are from people living in the 1800s. And by the time it exits the sun's gravitational influence entirely around the year 10,000, human civilization will have transformed beyond recognition or ceased to exist or spread across the galaxy, or been replaced by our AI descendants or experienced any of countless other futures we can barely imagine from our current vantage point. 3I Atlas will continue its journey through interstellar space, travelling for millions or billions of years until it enters some other star system, where perhaps other intelligent observers will detect it and will debate whether it's natural comet or ancient artifact from the civilization that once inhabited the system it passed through eons earlier. We'll debate the same questions we're debating. We'll examine the same kinds of statistical anomalies. We'll argue about compound probabilities and Occam's razor, and the balance between open-minded investigation and skeptical rigour, carrying whatever mysteries we couldn't unlock in the brief months we had to study it. Let's step back and ask the bigger question that contextualizes why 3I Atlas matters beyond the immediate fascination of an interstellar visitor with unusual properties. Why should we care about this one object when there are billions of celestial bodies we could study? Why dedicate observational resources and analytical effort to tracking its trajectory and measuring its jets when those resources could be used for other scientific investigations? First reason, 3I Atlas represents our best opportunity yet to study material from another stellar system without building interstellar spacecraft ourselves. We're decades or centuries away from having technology to send probes to even nearer stars. Voyager 1, humanity's most distant spacecraft, has been travelling for 45 years and has just barely exited the solar system. At its current velocity, it would take 70,000 years to reach Proxima Centauri, our nearest stellar neighbour. We're not visiting other star systems anytime soon with current or near-term technology. But interstellar visitors come to us, bring material that formed in other stellar environments, carry compositional signatures that reveal conditions around other stars, provide natural samples from exoplanetary systems that we could study in detail if we could collect them, or at minimum observe closely while they pass through our solar system. Every spectrum we capture of 3I Atlas, every photometric measurement we make, every image we process, tells us something about conditions around other stars. The composition reveals what elements were available in the protoplanetary disk where it formed. The structure reveals what temperatures and pressures and impact histories shaped its evolution. The behavior under solar heating reveals how volatile distributions and sublimation physics work in objects that didn't form in our solar system and that might have experienced different conditions than solar system comets. All of this informs our models of planetary system formation across the galaxy, helps us understand whether the solar system is typical or unusual, constrains theories about how often certain compositions or structures arise, provides ground truth for exoplanet studies, where we're trying to infer planetary compositions from indirect observations. 3I Atlas is like free sample from distant stellar system delivered to our doorstep for study. Second reason, it's establishing protocols for how we study rare, transient phenomena that require rapid, coordinated response from multiple instruments and institutions. Oumuamua caught us off guard in 2017. By the time we recognized it as interstellar visitor and mobilized observational resources, it was already receding and fading. We had just days of useful observation before it became too faint to study with most telescopes. That was a painful lesson in how unprepared we were for detecting and characterizing interstellar objects, despite having discussed the possibility theoretically for decades. 2I Borisov was better when it arrived in 2019. We detected it earlier in its solar system passage, had more time to coordinate observations, collected more data. But its trajectory wasn't optimal for Earth-based observation, Geometric configurations meant we couldn't observe it during some critical periods, and we were still learning how to coordinate international efforts to maximize scientific return. 3i Atlas has been perfect from observational standpoint. Discovered early in July 2025 when it was still far from perihelion, trajectory brought it relatively close to Earth at times when observing geometry was favourable. Has been observed extensively by Hubble, by ground-based telescopes worldwide, by spectroscopic instruments capturing composition, by photometric monitoring tracking brightness variations. Documented by multiple instruments across multiple wavelengths from radio through visible to infrared. We've built comprehensive data set capturing its properties throughout its journey through inner solar system. Whatever else 3i Atlas is, natural comet or something more exotic, it's masterclass in coordinated astronomical observation. It's demonstration that when international community identifies object of high scientific interest and mobilizes resources appropriately, we can collect data quality and completeness that enables real understanding rather than leaving us with tantalizing hints and frustrating gaps. The protocols we've developed and refined through 3i Atlas observations will serve us well when the next interstellar visitor arrives, and there will be more. Detection capabilities are improving. We're more likely to spot these objects early. We need to be ready with institutional frameworks and observational strategies that maximize what we learn from each opportunity. Third reason, and this is where Loeb's work becomes particularly important and particularly controversial. 3i Atlas is forcing us to develop better frameworks for evaluating anomalous data. How do we balance the principle that extraordinary claims require extraordinary evidence with the equally important principle that we shouldn't dismiss statistically significant anomalies just because they're uncomfortable? How do we maintain scientific rigor that guards against false positives, claiming discoveries that aren't real, while also avoiding false negatives, missing real phenomena because we're too conservative about what we're willing to seriously investigate? The compound probability calculations Loeb presents aren't wild speculation, aren't numerology or pattern matching or motivated reasoning designed to support predetermined conclusion. They're straightforward statistical mechanics applied to geometric observations. We measure the rotation axis alignment. We calculate the probability that such alignment would occur randomly. We measure the trajectory alignment with ecliptic plane. We calculate that probability. We combine them according to standard probability theory. The mathematics is simple and transparent. Anyone can verify the calculations. If the geometries and behaviors we observe have probabilities of occurrence at 1 in 10,000 or worse, under the natural hypothesis, that's information. That's signal. That's data demanding explanation. It might be signal of natural processes we don't fully understand yet. Maybe there's some astrophysical mechanism that preferentially produces these alignments in ways our current models don't capture. It might be signal of selection bias in our detection methods. Maybe we're more likely to detect interstellar objects with certain geometric properties, skewing our sample toward unusual configurations. It might be signal of something else entirely that we haven't considered because we're limited by our imagination and by our experience with the relatively small sample of objects we've characterized. But it's signal. It's not noise. It's not measurement error. It's not something we can responsibly ignore while claiming to be doing rigorous science. Good science follows the data wherever it leads, even when it leads somewhere uncomfortable, even when it challenges assumptions we're invested in, even when it forces us to take seriously hypotheses that seem implausible or that we'd prefer to dismiss because accepting them would complicate our worldview. This is why Loeb's advocacy for the Galileo project matters beyond just the specific question of whether 3i Atlas is natural or artificial. He's establishing precedent that anomalous observations deserve investigation proportional to their improbability, that 1 in 10,000 compound probabilities merit more than just probably natural, let's move on, that science should be allocating resources to understanding these anomalies, building dedicated instruments, designing observation campaigns, conducting modelling studies, testing specific hypotheses in proportion to how unlikely they are under standard explanations, not because we assume they're artificial. Not because we're jumping to conclusions, but because 1 in 10,000 observations are by definition exceptional, and exceptions are where we learn things, where paradigms shift, where our understanding expands beyond what current models predict. Whether that expansion reveals new natural mechanisms or reveals something more exotic, we only find out by investigating rather than assuming. So what should we make of the January 7th Hubble image and the triple jet mystery it reveals? Let me summarize what we know with high confidence, what we suspect with varying degrees of certainty, and what remains genuinely unknown despite extensive observation and analysis. This is important because conflating these categories, treating hypotheses as facts or treating uncertainties as settled questions, is how scientific communication goes wrong and how public understanding gets distorted. What we know with high confidence, meaning these are direct observations that multiple, independent instruments have confirmed and that aren't subject to significant interpretation uncertainty. 3i Atlas is displaying a triple jet structure with 120-degree symmetry. This is visible in processed Hubble images, is confirmed across multiple observation epochs, is real geometric feature of the object rather than being instrumental artifact or processing mistake. The dominant antitail points sunward across distances of 400,000 kilometers. This isn't optical illusion. We've verified this through observations at multiple viewing angles that would reveal projection effects if they were responsible for the apparent sunward extension. The antitail is real physical structure. The rotation axis is aligned within 6 to 8 degrees of the sunward direction. This is derived from wobble analysis of the antitail over multiple rotation periods, combined with geometric constraints from the collimation. Measurement has uncertainties, but the basic conclusion is solid. The trajectory is aligned within 5 degrees of the ecliptic plane. This is simple orbital mechanics calculation from positional observations, is as certain as any orbital determination. The compound geometry has probability approaching 1 in 10,000, under assumption that rotation axis orientation and trajectory orientation are independent and random. This is mathematical consequence of the individual probability estimates. If you disagree with conclusion, you need to either challenge the individual probability estimates or explain why the independence assumption is wrong. No radio signals have been detected despite sensitive SETI observations by Breakthrough Listen. This rules out certain classes of artificial hypotheses, but doesn't definitively establish natural origin for reasons we've discussed. Multiple aspects of the object's composition and behavior match natural comets: water ice, carbon dioxide ice, cometary coma structure, outgassing that responds to solar heating, but with unusual characteristics that include compositional anomalies like high nickel-to-iron ratio and geometric anomalies like the triple jet symmetry and sunward anti-tail. What we don't know, meaning these are open questions where evidence is ambiguous or insufficient, whether the geometric alignments are coincidental or indicative of underlying physical principles we haven't identified. Maybe there's some reason why interstellar objects preferentially have their rotation axes aligned with their trajectories. Maybe formation processes or ejection mechanisms from home stellar systems impart correlations between rotation and trajectory that our current models don't predict. Maybe the sample size is too small and we're seeing statistical fluctuation that would average out if we had larger sample. All possibilities worth investigating but currently uncertain. Whether the antitail is maintained by exotic gas dynamics we don't understand, by unusual ice distribution creating persistent sublimation from polar regions, by some other natural mechanism, or by something artificial. We have observations showing the antitail exists and persists. We don't have definitive explanation for how it's maintained against dispersive forces that should cause it to expand and fade. Whether the triple jet symmetry reflects underlying structure of the nucleus, maybe it's perfectly symmetric natural object with threefold crystal structure, somehow scaled to kilometer dimensions, or reflects engineered design for functional purposes, or is coincidental arrangement of active regions that happens to show symmetry at this time, but might not maintain it over longer periods. Whether continued observation will reveal additional anomalies that make natural explanation even more strained, or whether observations will resolve existing anomalies through natural explanations, we discover as we learn more about how interstellar objects behave. The March-Jupiter encounter is a crucial test. Daughter object release would tip scales dramatically toward artificial. Absent daughter objects tips toward natural while not definitively proving it. What Professor Avi Loeb advocates for and what this channel supports is proportional investigation. Anomalies with compound probability of 1 in 10,000 deserve scientific resources proportional to that improbability. Not to prove preconceived conclusions, not to claim we found aliens before evidence justifies that claim, but to understand what we're actually observing through dedicated investigation that takes the anomalies seriously, rather than dismissing them prematurely. The January 7th Hubble image is the clearest documentation yet of behaviour that challenges standard cometary physics. The triple jet configuration visible after Larsen-Cicconnina filtering. The 400,000 km sunward anti-tail that persists despite decreasing solar heating. The geometric relationships that stack multiple low probability alignments in single object. Whether that challenge reveals gaps in our models of how comets work, unusual but natural phenomena that we haven't characterized before because our sample size is small, or something more exotic than natural comet, remains open question, but it's question worth asking, question worth investigating, question worth taking seriously, because the universe is under no obligation to make sense to us on our preferred timescales or through our preferred explanations. It is what it is. Our job as scientists and as informed observers is to observe it accurately, analyze it honestly, and follow the data wherever it leads, even when it leads somewhere unexpected, even when it makes us uncomfortable, even when it challenges assumptions we've held for decades or centuries. The alternative, deciding in advance what answers are acceptable and filtering observations to match those preconceptions, isn't science. That's ideology. That's allowing our preferences to override evidence. That's the mistake that scientific method was specifically designed to prevent through its emphasis on empirical observation, testable predictions, and willingness to revise theories when observations contradict them. So we watch, we measure, we analyze, we debate interpretations while acknowledging which aspects are firmly established versus which are speculative. We wait for the March Jupiter encounter to test Loeb's daughter object prediction. We continue collecting data while 3i Atlas remains observable. We build better instruments and better protocols for studying future interstellar visitors. We remain simultaneously skeptical of extraordinary claims and open to extraordinary observations. We do science the way science is supposed to be done, following evidence rather than assumptions, testing hypotheses rather than defending dogmas, seeking truth rather than comfort. If you found this deep dive into Professor Loeb's research valuable, if you appreciate the effort to present scientific analysis without hype, but also without dismissing genuine anomalies just because they're uncomfortable, hit that subscribe button right now. We're building a community of people who want to understand cutting edge of astrophysics without dumbing it down, but also without the tribal dynamics that sometimes infect scientific discourse, where taking certain positions becomes socially costly regardless of what evidence shows. This channel is about the science, about the observations, about the mathematics, about following data wherever it leads without predetermined conclusions about where we want it to lead. About maintaining both rigor and openness, about being skeptical of claims that aren't supported while being willing to seriously investigate observations that are anomalous, about understanding that both false positives and false negatives are mistakes we want to avoid. Claiming discoveries that aren't real is bad, but missing real phenomena because we're too conservative is also bad. Drop a comment with your thoughts. Do you think 3i Atlas's anomalies indicate natural processes we don't understand or something else? What would convince you either way? What observations would shift your probability distribution decisively toward natural or toward artificial? How should science balance the competing risks of being too credulous versus too dismissive when evaluating anomalous data? These are hard questions without obvious answers, and hearing diverse perspectives from people who care about getting it right, rather than about defending particular positions, is valuable. Share this with anyone interested in serious scientific analysis of interstellar objects, with anyone who wants to understand the actual evidence and the actual statistical arguments, rather than getting simplified version that either dismisses everything as definitely natural or sensationalizes everything as proof of aliens. The truth, as usual, is more nuanced and more interesting than either extreme position acknowledges. Check the description for links to all the sources cited in this analysis. Loeb's Medium articles where he presents his detailed mathematical arguments. NASA's Hubble data releases showing the raw images and processed versions. The breakthrough Listen paper describing their radio observations and null results. The Ricard Licandro paper in Astronomy and Astrophysics documenting the wobble analysis. Everything cited here is publicly accessible. Everything can be verified. This isn't asking you to trust my interpretation. This is providing you with access to primary sources so you can evaluate the evidence yourself and reach your own conclusions. That's how science communication should work, not telling you what to think, providing you with the information and the context needed to think for yourself, explaining the arguments on different sides, acknowledging uncertainties, distinguishing between what's firmly established and what's speculative, letting you decide what probability distribution makes sense to you given the evidence and given your priors about what's plausible. My role isn't to convince you that 3i Atlas is natural or artificial. My role is to explain what we've observed, what those observations mean, what different interpretations exist, what evidence supports or challenges each interpretation, and what future observations might resolve the uncertainties. To present the science accurately and comprehensively enough that you can understand the debate and participate in it as informed observer rather than as passive recipient of conclusions that others have reached. Because ultimately, questions about whether we're alone in the universe, whether artificial objects are visiting our solar system, whether our understanding of cometary physics is complete or has gaps that anomalous objects are revealing, these are questions that affect everyone. These aren't just academic puzzles for specialists to debate. These are questions about humanity's place in cosmos, about what exists beyond Earth, about what we might encounter as we develop spacefaring capabilities, about how we should interpret anomalous observations when they challenge our models. Everyone has stake in getting these questions right. Everyone deserves access to the evidence and arguments. Everyone should be able to follow the investigation and understand what's being claimed and what supports those claims and what remains uncertain. Science communication that treats public as too unsophisticated to handle complexity or ambiguity is doing everyone disservice. Most people are perfectly capable of understanding nuanced arguments if they're presented clearly and honestly rather than being dumbed down or sensationalized. So that's what we do here. Clear, honest presentation of what we know and what we don't know and what evidence supports different positions. Trust that you're intelligent enough to handle complexity and uncertainty. Respect for your ability to evaluate arguments and reach your own conclusions. Confidence that pursuing truth wherever it leads is better than pursuing comfortable conclusions that might be wrong. Stay curious. Stay skeptical. Stay open to wherever the data leads. Don't let anyone tell you that asking questions about anomalous observations is unscientific, or that taking seriously the possibility of artificial origin is crazy. Loeb is Harvard professor with decades of research contributions to astrophysics. His analysis of 3i Atlas's statistical anomalies is rigorous mathematics applied to well-characterized observations. Dismissing it without engaging with the actual arguments is the opposite of scientific thinking. But also, don't let anyone tell you that anomalous observations prove artificial origin, or that we should jump to conclusions before evidence justifies them. Extraordinary claims do require extraordinary evidence. The bar for claiming we've detected alien artifact is appropriately high. We're not there yet with 3i Atlas. Whereas this object shows statistical anomalies that deserve serious investigation to determine whether they reveal natural processes we don't understand or something more exotic. That's honest assessment of where we are. That's acknowledgement of both the genuinely anomalous observations and the substantial uncertainties that remain. That's how science works when it's working well, moving toward truth through accumulation of evidence and through testing of competing hypotheses rather than through premature closure on answers we find comfortable or exciting. The March 16th Jupiter encounter is less than 2 months away as I record this. That's not long in cosmic terms, but it's enough time for anticipation to build, for additional observations to be collected, for analyses to be refined and published. The predictions are on the table. Loeb has stated clearly and publicly that daughter object release into Jupiter orbit would constitute strong evidence for technological origin. That's falsifiable prediction. That's what good science looks like, making specific claims about what we should observe if hypothesis is correct, then letting observations determine whether hypothesis survives or falls. If we observe objects separating from 3i Atlas during the Jupiter encounter, if those objects enter stable orbits around Jupiter, rather than continuing on hyperbolic trajectories, if we can track them over subsequent weeks and months, confirming they're genuinely orbiting, rather than just appearing to orbit due to projection effects or temporary gravitational perturbations, then we have phenomenon that's extraordinarily difficult to explain naturally. Would require multiple simultaneous gravitational captures, events that are individually extremely unlikely, and that occurring together would be vanishingly improbable. Or would require acknowledging that 3i Atlas possesses propulsion capability that enables controlled release and orbital insertion of smaller objects. At that point, the probability distribution shifts dramatically. Not to certainty of artificial origin. You could still construct scenarios involving fragmenting comet, where fragments happen to have exactly right velocities for capture, though such scenarios become increasingly contrived. But to high enough probability that serious institutional resources should be allocated to investigating technological hypothesis. We'd want to track the daughter objects extensively. Monitor for any emissions or behaviours that might reveal their nature. Look for patterns in their orbits or configurations that might indicate function or purpose. Essentially treat them as potential artifacts requiring comprehensive characterization rather than as curiosities to be noted and filed away. If we don't observe daughter objects, if 3i Atlas simply passes Jupiter with only the gravitational deflection that Newtonian mechanics predicts, if its trajectory after the encounter matches computational models within observational uncertainties, then the technological hypothesis takes significant hit. Doesn't die entirely because absence of daughter objects doesn't prove natural origin any more than their presence would prove artificial origin, but makes natural explanation more parsimonious. Reduces the probability that we're observing spacecraft or probe because the behaviour matches what natural comet would do, rather than what mission profile for studying Jupiter system would require. Either way, we learn. Either way, the possibility space narrows. Either way, future observations become more informative because they're testing specific predictions, rather than just collecting data without clear hypotheses about what that data means. That's scientific progress. That's how uncertainty gradually resolves into understanding through accumulation of evidence that favours some explanations over others. The observations that amateur astronomers and astrophotographers can contribute shouldn't be underestimated. Professional telescopes have scheduled observing programs. Can't dedicate unlimited time to single object, no matter how interesting. But distributed network of amateur observers with good equipment can provide continuous monitoring that professional facilities can't match. Can catch transient events that might occur between scheduled professional observations. Can build temporal coverage that fills gaps and that might reveal behaviours that would be missed if we only looked during scheduled observation windows. If you have 8-inch or larger telescope, if you're experienced with astrophotography and image processing, if you have access to dark skies away from light pollution, you can observe 3i Atlas during its opposition on January 22nd and during the weeks afterward as it continues outbound toward Jupiter. You won't see the kind of detail that Hubble captures. You need space-based telescope above atmosphere to get that resolution and that sensitivity, but you can contribute to the temporal coverage, can add data points to the light curve, can potentially detect variations or outbursts that might correlate with rotation, or with distance from Sun, or with other factors that professional observations aren't sampling densely enough to catch. And if you do observe, if you collect images, share them with the community, post them on astronomy forums, send them to researchers who are actively studying the object, contribute to the public dataset that enables independent analysis and verification. Science works best when observations are shared openly rather than being hoarded or kept private. When multiple people can examine same data and can test whether their analyses reach same conclusions. When transparency and replication are values that the community upholds, rather than being afterthoughts. The long-term trajectory of 3i Atlas beyond the Jupiter encounter becomes increasingly uncertain as we project further into the future, not because the physics is uncertain. Orbital mechanics is deterministic, and we can calculate trajectories with high precision given sufficient observational data, but because we don't know what non-gravitational forces might operate. If the object is natural comet, outgassing as it recedes from the Sun will create weak rocket effect that gradually perturbs trajectory in ways that depend on rotation state and activity level and ice distribution. If it's artificial with propulsion capability, trajectory could change in ways that orbital mechanics alone doesn't predict. So predictions about exactly when it reaches Saturn or Uranus or Neptune carry increasing uncertainty. The nominal trajectory based on current observations and assuming no non-gravitational forces beyond what we've already measured suggests Saturn encounter in late 2026, Uranus in 2027, Neptune in 2028. But those dates could shift by months or even years depending on what happens during and after Jupiter. We'll need to continue tracking the object, refining orbital elements as new observations become available, updating predictions as actual trajectory data replaces extrapolations from earlier measurements, Each planetary encounter provides opportunity for gravitational deflection that alters the trajectory. Each also provides opportunity for close-range observation if we have spacecraft in those systems with cameras that can be pointed at 3i Atlas as it passes. We don't have active missions at Uranus or Neptune currently. Voyager 2 passed them decades ago and is now in interstellar space, and no follow-up missions have reached those systems. But we do have Juno orbiting Jupiter. Depending on geometric configurations during the March encounter, depending on whether Juno's orbital position allows useful viewing angles, we might get much closer images of 3i Atlas than Hubble can provide from Earth's vicinity. That's worth hoping for, even though mission teams have their own science priorities and can't necessarily divert resources to observing interstellar visitor. But if the encounter geometry is favourable, if capturing images wouldn't interfere with Juno's primary mission objectives, the scientific value of close-range observations of anomalous interstellar object might justify allocating some observation time. We'll have to wait and see whether that opportunity materializes or whether our best views remain from Earth-based and Earth-orbital telescopes. The implications of 3i Atlas for our understanding of interstellar object populations extend beyond just this single visitor. We now have 3 confirmed detections: Oumuamua in 2017, 2i Borisov in 2019, 3i Atlas in 2025. That's 3 detections in 8 years. Not a huge statistical sample, but enough to start estimating how common such visitors are and what fractions show unusual properties versus appearing like typical comets. Oumuamua was anomalous, showed non-gravitational acceleration that couldn't be explained by outgassing in standard cometary model, because no cometary coma was detected despite acceleration magnitude suggesting substantial gas emission would be required, showed elongated shape or tumbling rotation that created unusual light curve, showed trajectory that brought it close to inner solar system for detailed observation, multiple anomalies that generated extensive debate about natural versus artificial origin, debate that remains unresolved because object faded before conclusive data could be collected. 2i Borisov appeared much more normal, showed active cometary coma with gas and dust emission at rates consistent with solar heating, showed composition similar to solar system comets, though with some unusual features like high carbon monoxide abundance, showed no obvious geometric anomalies or behaviours that challenged natural interpretation, was exactly what you'd expect from ordinary comet that happened to originate in another stellar system. Similar physics, similar chemistry, similar behaviour under solar heating. 3i Atlas is back to anomalous. The triple jet geometry, the sunward anti-tail, the rotation axis alignment, the trajectory alignment with ecliptic, the compositional oddities, the persistence of structures that should be transient, multiple features that individually are rare and that combined are extremely rare under natural hypothesis. Whether these represent natural processes we don't understand yet or indicate artificial origin remains debatable, but anomalous relative to standard cometary model is undeniable. So we have 2 anomalous detections and 1 normal detection in sample of 3. That's 67% anomalous rate. Now obviously we can't draw strong conclusions from such small sample. Percentage could easily be coincidence of drawing unusual examples early in our detection program. But it raises questions. Are interstellar objects more diverse than solar system comets? Do formation conditions in other stellar systems produce objects with properties we don't see in our own comets? Are we detecting anomalous objects preferentially because they're more visible or more interesting, and therefore get more observation time and more detailed analysis? Or is the anomalous rate actually telling us something important? That substantial fraction of interstellar visitors aren't purely natural. That some fraction of objects transiting between stellar systems are artificial probes, or artifacts rather than being random ejecta from planetary formation processes. We can't answer definitively with current data, but the question is legitimate and deserves investigation as sample size grows. As our detection capabilities improve, as LSEST, Legacy Survey of Space and Time, comes fully online with its ability to scan entire visible sky repeatedly and detect faint moving objects with unprecedented efficiency, we'll find more interstellar visitors, maybe dozens per year rather than 1 every few years. We'll build statistical sample that allows meaningful characterization of the population. We'll be able to determine what fractions show anomalous properties. We'll be able to test whether anomalies cluster in particular types of objects, or particular trajectories, or whether they're uniformly distributed. we'll develop better intuition for what's normal versus what's exceptional in interstellar visitor population. That data will help resolve debates about specific objects like 3i Atlas. If we find that 30% or 50% of interstellar visitors show multi-jet configurations with symmetry, then 3i Atlas's triple jets become less remarkable, just one example of common though previously unrecognized phenomenon. If we find that 1% show such features, then 3i Atlas's geometric properties remain highly anomalous, requiring special explanation, either through rare natural circumstances or through artificial origin. Similarly, if we find that rotation axis alignments within 10 degrees of sunward direction occur in 5% or 10% of interstellar objects, then maybe there's natural mechanism we don't understand that creates such alignments more frequently than random chance predicts. If we find they occur in 0.5% as random chance predicts, then 3i Atlas's alignment remains statistically significant anomaly, demanding explanation. Building that statistical foundation requires patience and sustained observation programs and funding that supports long-term monitoring rather than just responding to immediate exciting discoveries. Requires institutional commitment to characterizing populations rather than just studying individual interesting examples. Requires recognizing that understanding what's normal is prerequisite for recognizing what's exceptional. All things that astronomy community generally does well, but that require advocacy and resource allocation and strategic planning to implement effectively. The broader philosophical implications of the 3i Atlas observations and debates connect to fundamental questions about how we do science and how we update beliefs in response to anomalous data. The tension between Loeb's position that statistical anomalies deserve investigation proportional to their improbability and NASA's position that the object behaves like regular comet and doesn't warrant special treatment reflects deeper disagreement about epistemic standards and about how science should respond to observations that don't fit comfortable categories. From Bayesian perspective, both positions are defensible depending on priors. If you start with very low prior probability that artificial interstellar probes exist and visit our solar system, maybe because you think technological civilizations are extremely rare, or because you think even if they exist they don't send probes, or because you think even if they send probes the probability of encountering one is negligible, given the vastness of space, then you need very strong evidence to shift your posterior probability significantly toward artificial hypothesis. The geometric anomalies alone might not be sufficient to overcome very strong prior against artificiality. If you start with less extreme prior, maybe you think technological civilizations are moderately rare but that over galactic history enough have arisen that probe populations might exist, or maybe you're agnostic about probe frequency and willing to let observations drive your beliefs rather than starting with strong assumptions, then the compound statistical anomalies combined with the specific geometric features might shift your posterior probability enough that serious investigation is warranted even if you're not yet claiming high confidence in artificial origin. Neither position is irrational. Reasonable people can disagree about priors, can have different intuitions about how probable various scenarios are before seeing evidence. Bayesian framework tells us how to update given evidence, but it doesn't tell us what priors to start with. That depends on background knowledge and experience and judgment that different people reasonably bring to questions. What's not reasonable is ignoring the evidence, is refusing to update priors at all regardless of what observations show, is dismissing statistical anomalies without engaging with the calculations or providing alternative explanations for the observations. That's not Bayesian updating. That's not scientific reasoning. That's defending fixed beliefs against contrary evidence, which is exactly what scientific method was designed to prevent. The institutional dynamics that make it professionally costly for researchers to take artificial hypothesis seriously, even when evidence merits investigation, are worth examining because they affect how science progresses. Loeb has tenure at Harvard, has established reputation with hundreds of publications in top journals, has credibility that insulates him from worst consequences of being associated with controversial topics. He can advocate for investigating artificial origins without destroying his career because his status is already secure. But early career researchers don't have that protection. Postdocs looking for faculty positions, graduate students writing dissertations, junior faculty seeking tenure. For them, being associated with alien probe research can be career-limiting even if the research is rigorous and scientifically valid. Telescope time allocation committees are skeptical. grant review panels are conservative. Hiring committees worry about reputation effects. Publication venues prefer mainstream topics that don't generate controversy. So the research that most needs doing, rigorous investigation of anomalous observations to determine whether they indicate natural processes we don't understand or something more exotic, doesn't get done at the scale it deserves because incentive structures discourage it. The people who could do it most effectively are precisely the people who face highest cost for doing it. Creates systematic bias where anomalous observations get less investigation than their statistical significance warrants, because investigating carries professional risks that studying conventional topics doesn't. This is unfortunate because it means we might miss important discoveries, might fail to recognize artificial visitors even if they're present because we've created an environment where seriously investigating that possibility is professionally dangerous, might continue dismissing anomalies as probably natural, not worth detailed study, when accumulated evidence justifies greater investment of attention and resources, might let our institutional incentives override our scientific values in ways that compromise our ability to follow evidence wherever it leads. The solution isn't to eliminate skepticism or to make it equally easy to publish speculative claims as to publish well-supported findings. Scientific quality control serves important function. Peer review and editorial standards and grant review and tenure evaluation all exist for good reasons, to ensure that limited resources get allocated to highest quality research and that published findings meet standards of rigor and evidence. We don't want to eliminate those filters, but we do want to ensure that the filters aren't systematically biased against investigating anomalous observations just because investigating might reach uncomfortable conclusions. Want to ensure that statistical significance is recognized as valid criterion for allocating investigative resources, regardless of whether investigation confirms conventional wisdom or reveals something unexpected. Want to ensure that early career researchers can pursue important questions without career suicide. That requires cultural change in scientific institutions, requires leadership from senior researchers like Loeb, who have standing to advocate for different standards without personal risk. Requires funding agencies being willing to support investigation of controversial questions when the scientific case for investigation is sound. Requires journals being willing to publish rigorous analyses of anomalous data, regardless of whether conclusions align with editor preferences. Requires tenure committees evaluating research quality rather than research topic safety. All difficult institutional changes that don't happen quickly or easily, but worth working toward because the alternative, systematic bias against investigating observations that might reveal paradigm-shifting discoveries, is unacceptable for community that claims commitment to following evidence wherever it leads. Science should be method for discovering truth, not method for defending comfortable conclusions against inconvenient observations. The public interest in 3i Atlas, and in the broader question of whether artificial objects visit our solar system, reflects deep human concern with whether we're alone in the universe. This isn't idle curiosity. This is one of the most profound questions humans can ask. Connects to our self-understanding, to our place in cosmos, to our future as potentially spacefaring species, to fundamental questions about life and intelligence and whether these are common or rare in the galaxy. For centuries we've looked at stars and wondered whether others are out there, whether life arises on other worlds, whether intelligence and technology emerge elsewhere, whether civilizations like ours or vastly more advanced exist among the billions of stars in our galaxy. These questions were purely speculative for most of human history. We could wonder, but we had no way to know. Now we're developing capabilities to actually investigate, to detect exoplanets and analyze their atmospheres for biosignatures, to search for radio signals or optical beacons that technological civilizations might transmit, to observe interstellar visitors that might represent either natural samples from other stellar systems or artificial artifacts from technological species. The transition from speculation to observation, from wondering to actually testing hypotheses about cosmic life and intelligence, is one of the great intellectual achievements of our time, and that makes how we handle anomalous observations particularly important. When we encounter something like 3i Atlas that shows features we don't expect, that challenges our models, that might indicate something extraordinary if we're willing to take the observation seriously, we're at decision point. Do we investigate thoroughly to determine what we're actually observing? Or do we default to conventional explanation without doing the work to verify whether that explanation actually accounts for all the data? The answer should be obvious. We investigate. We test hypotheses rigorously. We collect additional data that might distinguish between competing explanations. We follow the evidence. But institutional and social pressures sometimes push toward dismissal rather than investigation, toward conserving resources and protecting reputations rather than pursuing truth wherever it leads, toward maintaining comfortable paradigms rather than confronting observations that might require revising our understanding. Resisting those pressures requires individual courage and institutional support and public engagement that values truth-seeking over comfort-seeking. That's why channels like this exist. That's why communicating science accurately and comprehensively, rather than sensationalizing or dismissing anomalies, matters. That's why your engagement through subscribing and commenting and sharing helps. It demonstrates that public cares about these questions and wants rigorous investigation, rather than premature closure on answers that might be wrong. So here's where we are as I conclude this analysis of the January 7th Hubble image and the triple jet mystery it reveals. We have objects showing multiple statistical anomalies. Rotation axis aligned within 6-8 degrees of sunward direction with 0.205% probability. Trajectory aligned within 5 degrees of ecliptic plane with 0.2% probability. Compound probability approximately 1 in 10,000. Triple jet geometry with perfect 120-degree symmetry. Sunward anti-tail extending 400,000 kilometers and persisting across months despite decreasing solar heating. Compositional oddities including high nickel-to-iron ratio, all documented through rigorous observations by multiple instruments. We have natural explanation that accounts for some observations but struggles with others, particularly the geometric alignments and their compound improbability. We have artificial hypothesis that would account for geometric alignments through deliberate design, but that lacks direct supporting evidence like radio emissions or obvious artificial structures. We have upcoming Jupiter encounter in March that provides test of daughter object prediction that could shift probability distribution substantially in either direction, depending on what we observe. We have scientific debate between researchers taking different positions based on different assessments of evidence and different prior beliefs about what's plausible. We have institutional biases that make investigating artificial hypothesis professionally risky despite statistical case for investigation being sound. We have public interest that reflects genuine concern with profound questions about humanity's cosmic context. We have opportunity to do science right, to follow evidence, to test predictions, to update beliefs based on observations rather than preferences. The January 7th image is remarkable documentation of behavior that challenges our understanding of how interstellar visitors work. Whether that challenge ultimately reveals natural mechanisms we haven't characterized, or something more exotic remains to be determined through continued observation and analysis. But it's a question worth asking, worth investigating, worth taking seriously. Because the universe doesn't care about our comfort or our assumptions. It is what it is. And our job is to figure out what that is through honest investigation, rather than through defending preconceptions. Thank you for watching this deep dive into some of the most anomalous observations in modern astronomy. If you found it valuable, the subscribe button is right there. This channel exists to examine cutting-edge astrophysics without hype, but also without dismissing genuine anomalies, to present evidence and arguments from multiple perspectives, to help you understand what we know, what we don't know, and what might be discovered through continued investigation, to treat you as an intelligent audience capable of handling complexity and uncertainty rather than needing everything simplified to false certainties. The comment section is for thoughtful discussion. Share your perspective on whether the statistical anomalies warrant the investigation Loeb advocates, or whether natural explanation is sufficient despite improbabilities. Discuss what the March Jupiter encounter might reveal and what you think the observations would mean. Engage with others respectfully even when you disagree. This is how communities build understanding, through dialogue that values truth over tribalism and evidence over ideology. And share this with anyone who wants to understand the real science rather than getting sensationalized version or dismissive version. The truth about 3i Atlas is genuinely fascinating without needing exaggeration. The statistical arguments are compelling without needing to claim they prove anything definitively. The observation quality is excellent and the debate is substantive and the future observations are promising. That's enough. That's the story worth telling accurately and comprehensively. Stay curious, stay skeptical, stay open. The universe is vast and ancient and full of wonders we're only beginning to understand. Some of those wonders will fit our models, some will force us to expand our models, some might reveal that reality is stranger than we imagined. The only way to find out which is to keep observing, keep measuring, keep testing hypotheses against evidence, keep following data wherever it leads. 3i Atlas is teaching us something, whether it's teaching us about exotic natural processes that produce low-probability geometric configurations or teaching us that artificial visitors are already here is still to be determined. But either answer expands our understanding. Either answer is discovery worth making. Either answer moves us closer to truth about the cosmos we inhabit and our place within it. I'll see you in the next one, when we'll have more data, more observations, more constraints on what this remarkable object represents. Until then, clear skies and may your telescopes reveal wonders.